All right, welcome back. This is lecture 3.3b. If you remember, we've been talking about how to find derivatives. And we started out with four rules in class on Monday: the constant rule, the sum difference rule, the multiplier rule, and the power rule. And last night's video, you talked about how these four rules could actually help you out in some more complicated situations, particularly with negative exponents and fractional exponents. Well, today's lecture, we're going to talk about two more rules. They're called the product rule and the quotient rule. But before I jump into what the rules are, I want to try convincing you why the rules are really necessary. So look at these three functions, f, g, and h. How would you go about finding the derivative of these functions? So I don't know about you, but I came up with a few ideas. My first idea was to FOIL and then use the derivative rules from class yesterday. But that really would only work for this first one, because then I could use like the power rule and all that stuff. Unfortunately, I don't know how to do that for g and h, partly because I don't really know what the derivative of sine is. So if I really needed to find the derivative of g or h, maybe I could use the limit definition, and that was my second idea. Remember that the derivative rules are a shortcut. They're not the only way, and they're not really the real way. It's like a trick. The real way to find a derivative is using this limit and trying to simplify it. That's going to be pretty messy though, so I'm kind of hesitant to start that work. It's going to be a really long expression with sine and e to the x, and I don't know how it's going to work out. So my last idea was to maybe try and use my calculator, and we did a problem a little bit ago where we used the n-deriv function to try and graph it. Now, the downside to this last idea is that unless I'm really lucky, I probably am not going to get the exact derivative. It's not going to tell me the function. But I could at least get a sense for what the derivative might look like. Maybe I could guess the function family at least. Okay, so hopefully I've convinced you that while we do have a lot of strategies, we really don't know enough to find the derivative of these second two functions. Well, that's what this video is going to be about. I'm going to give you tools to do that. First, before we start, I'm going to cheat a little bit here. We're going to spend some time on trig functions, exponents, and logs next week, but I want you to be able to use just these four derivatives for the purposes of today's lecture. So I'm going to ask you to just trust me, well, actually just trust your calculator about these derivatives. So that last idea I had, the n-deriv feature, I want you to use that right now. Take out your calculator and use the n-deriv function to graph the derivative of the sine function. What that looks like is you go to y equals, you'll type in math h, which is n-deriv, then you're going to put the sine function in there, so sine of x, and then comma x, and comma x one more time. You're telling the calculator just to graph the derivative for each x value. If you have a TI-84, this might look a little different. But either way, when you go to the graph, it's then going to show you what the derivative looks like. Your job is to look at this graph and see if you can make an educated guess about what function the derivative is. And when you're done with sine, go back and do the same thing for cosine, for e to the x, for ln of x. Awesome. So hopefully you saw, at least based on the graph, that it looks like the derivative of sine is cosine. And the derivative of cosine is negative sine. If you missed the negative, go back and take a look. You'll notice that the initial graph is just kind of flipped over the axis. The derivative of e to the x is actually just itself, and the derivative of the natural logarithm function is 1 over x. Now, you may not completely believe me yet, right? What we just did was kind of an estimate. It was an idea. We don't know for sure, and you shouldn't feel convinced that these are the right derivatives until I really prove it to you, which I will do in class. But for now, I'm going to ask you just to trust me that these four are the derivatives of each function, and you need to put them in cram and memorize them. They're going to be super important both for this lecture and for the quiz on Friday. Great. Now that we've got that out of the way, let's get started with the first of the next two rules. It's called the product rule. The formal way to say the product rule is if u and v are differentiable functions and f of x is the product of u and v. So think about this. We're saying the function that we want to take the derivative of is two other functions being multiplied together. If that's true, then the derivative of the original function is actually not just the derivative of these two multiplied together. You might think that, but that's not actually how it works. The derivative of this product is going to be the first function times the derivative of the second one, plus the second function times the derivative of the first one. There are two other ways we can write this. Instead of writing the notation out like this in red, you could write that the derivative is u times v prime. Remember, v prime is just another way to say the derivative of v, and v is the second of our two functions. And then it would be plus v times u prime. Or you could say, and this is the one that I prefer, that I remember using it in school, u dv plus v du. And it sounds like nonsense unless you're in calculus, and once you're in calculus, you know exactly what that means. That's the product rule. You need to memorize the product rule, both what it means and the actual notation for it, and you can use any of these three. You should understand them all. Here's how we use the product rule. So take a look at this first function. If you look at this function, first of all, this is one of the ones that we said we didn't know how to do at the beginning of this video, precisely because of the sine problem. And then we learned that the derivative of sine is cosine, so we fixed that problem, but we still couldn't solve this derivative because it was being multiplied times x squared. Well, this is a beautiful situation to use the product rule. If you think about it, the function that we're starting with is the product of two other functions, x squared and sine of x. Because it's the product, we can use this little formula to find the derivative. Now, I'm going to be really particular about how you show your work. I keep saying calculus is a language, calculus is a language. This is the language of how you would explain the derivative. It's not just about getting the answer, it's about how do you say the reasoning that got you to your answer. So when we recognize by looking at this function that it's a product, the way that we write that down is we say given f of x equals x squared sine x, let u equal x squared and v equal sine of x. And you should recognize that u and v are those letters from the product rule. That's not just by chance that I'm using those. You are always going to use u and v, and you're always going to choose what to make them equal to. Now the purpose is that u times v should equal f of x. So here's the first part, there's the second part. Now skip a little space in your work because there's one other thing we're going to have to do, but I want to give you the big picture first. So if this is the function we start with, then we're going to let u be this and v be this. Then f of x is the same thing as u times v. And we could have said u of x because we're thinking of it as a function, or you can just call it u the same way we could call f of x just f. And this then, we've created this. This is a creative step that you take. It's not a right or wrong thing. You get to choose how you want to do it. If you choose well, it will be helpful. And since we see that f of x is u times v, the derivative of f of x, as in f prime of x, is going to equal u times the derivative of v plus v times the derivative of u. That's just the product rule. And notice I'm using one of those alternate notations. You could have used v prime instead of dv if you want, or dv dx if you prefer. So again, to recap the big picture, we started with a function, and then we took that function apart into two pieces and we called them u and v. And now we're using the product rule. The next step is just going to be to plug into this formula. And as soon as we do that and simplify, we'll have our derivative. But you should notice that we're not quite ready to plug in. I know what u is, which means in this blank space right here, I'm going to put x squared. But then I need to multiply it times dv, or the derivative of v. I don't know what that is, and that's why we left some blank space right here. So you want to go back up, and let's find those derivatives. These should be easy. If u is x squared, then the derivative of u is just 2x, and I just used the power rule from class. Similarly, if v is the function sine of x, the derivative of v is going to be cosine of x, because that's one of the ones that I asked you to memorize. Okay, now that we have all 4 pieces, we can plug in. U, we already said, was x squared. dv is cosine of x, and I'm just going to multiply it right here. And then I'm going to add v, which is sine of x, and I'm going to multiply that times the derivative of u, which was 2x. And that's what it looks like. Now, there isn't a ton to simplify because there's no like terms. I might write the 2x out front of sine, just to make it look a little nicer. But basically, this is our derivative. X squared cosine of x plus 2x times sine of x. Just like that. Okay, if this seems weird to you, I'm totally with you. This is a weird function to start with, and it might even be a little hard to believe that this really is the derivative. How could we try and confirm that for ourselves? Well, if you think about what the derivative means, one of the things we know about it is that there's a relationship between the derivative and the original graph. The outputs of this function tell us about the slopes of this one, which means that when we look at their graphs, there's a couple relationships that we should be able to see really easily, even if both graphs are kind of weird. So what if we tried this? I may not be totally convinced that I have the right derivative, so I'm going to try graphing both of them and seeing if the relationship between the two shapes makes sense based on what I know. Grab your calculator and type both of these functions in. I'm going to use Desmos. So here's what I got for the graph. I've got my 2 functions. This is the function, the original one, and it's pretty weird. I'm looking at a very small window right now, but when I zoom out, it starts to get really crazy. Now, without going into a ton of detail, basically what's happening is the sine graph is getting really high, so the amplitude is changing. But if I just go back into where I can kind of see the shape pretty well, and then I add the derivative function, so I'm just going to click here, and the blue is the derivative that we got using the product rule. Well, look at a couple things. When the red function has a max or a min, right there and right there, or a horizontal tangent, which happens right here, because notice that the shape of the red graph seems to be horizontal. At all 3 of these points, my derivative graph has an x-intercept. Furthermore, when my original graph is increasing, the y values of my derivative are positive. All of this is pretty convincing to me, because we know those relationships. That's supposed to happen. It's supposed to happen that whenever your original function is decreasing, the slope is negative. Whenever your original function has a maximum, the slope is 0, so the derivative should equal 0 or have a y value of 0. So what seemed very strange and algebraic and abstract, this product rule thing, actually seems to work, at least based on the graph. Well, I don't know if that convinced you or not, but we're going to keep practicing it. Let's do example B. Just like before, we'll start out with the original function, and then we're going to choose what we want u and v to be. I'm going to choose u to be e to the x, and v to be x cubed minus 4x. That's not the only way to start this problem. This is a choice I'm making, a judgment call. Now, the reason I made this choice is because I know that this function is e to the x times x cubed minus 4x, so I think I can use the product rule. From there, I find the derivative of u and v because I know I'm going to need that, and then I set up the product rule. And this first line is just kind of restating the reason that I chose u and v, because if you multiply them, they give you f of x. And this is just the formula, and then I need to just plug in each of the pieces. Make sure that you know where each of these came from. And then I'm going to simplify, which means just distributing the e to the x's on both sides. And after I distribute everything out, there are no like terms, so that's my derivative function, just like that. Follow this same process, set up your work the same way, and do the examples for you.